LR laboratory. So please,
University and LNS. I will have a very peculiar talk because I will discuss about the use of high power lasers for nuclear astrophysics. So this is like a summary of my talk. So I will start with some information about laser matter interaction, and I will discuss very briefly about possible impact on nuclear astrophysics, and I will discuss one experimental campaign that we did, actually two, and the results, and then some future projects. So very fast, because we are late and it's the last talk. So the laser amplification technique did big steps, and which actually granted the Nobel Prize for Physics in 2018 to Donna Strickland, Jerome Rowe, but it's say the final step of our work that they have been doing for decades. So this technique is actually probably 30 years old or something, and it's based, simply put, it's you have low energy nanojoule or something laser pulse, very short, compressed, so less than under 10 per second. Then you stretch it so you can safely amplify it. It gains energy, then you recompress it, and if you are good enough, you can focus actually hundreds of joules. This is a scheme from Texas petawatt laser, for example, and into very short time windows. So you have very high intensity in terms of watts per centimeter squared. So you have high energy focused in space and time. And when this happens, actually, there is so the interaction of the electromagnetic field of these so intense actually present different paradigms. So depending on the interplay between the intensity of the laser, the intensity that you are focusing on the target, and let's say the thickness of the target, more generally the characteristic length of the target, I would say. So this interplay between these two main quantities defines the regime of your interaction. So I will not go too much in detail because it's not the point of the talk here, but I will just give some example. So mostly this is the most say used technique is TNSA. I'll give a short description in a few moments. But this is let's say that with the development of laser technologies, and so more intense lasers are built, this paradigm, of course, is they are exploring different regimes of interaction. And also there are different setups that you can have. You can shoot a laser on a target which can be thin or thick, and you can accelerate ion. You can have some schemes where you accelerate ion and then you use them for with a secondary target, for example, or you can have some also some focusing on many lasers as a NIF, and you know this 2 days old news about NIF. I will not discuss about that, honestly. So this is just to give an overview of actually what still has to be explored, because we are now exploring new paradigms. Some are predicted, some actually. So a few words about these two common techniques. So TNSA, so basically what you do, you focus the laser on usually a thin target, and you accelerate the laser energy transfer to the electrons, which are somehow expelled from the target and are dragging the ions out of the target. And then so there is some two-step process where the energy is given to the electrons, and then it's the electric potential. You have a gradient and accelerate actually ions up to MeV energies. And this is a typical spectra. And this is used mainly in applications and say medical or other applications, mostly energy application too at some point. And this is another paradigm. When the intensity of the laser is high enough, the laser is directly, I would say, giving energy to ions. So you are not just stripping all the material, you are stripping the electron of the material, you are actually pushing the ions inside the target. And if it's thin enough, let's say, you can actually accelerate a bunch of ions directly. And this gives this kind of spectra. So if you, and this is also something that it's pretty new and it's still not fully understood, but the energy that we are and the spectra are not the typical spectra that we like in nuclear physics, of course, because it's a broad spectra, it's high energy. So this is not the paradigm that I am going to discuss. Because, as I was saying, this is the only things I would say about nuclear physics for now. So this is a slide that I stole around. And okay, we have seen this. There is not much to say. We know that the energy, of course, all the reaction here happens below the Coulomb barrier. So it's tunneling, and we know some example, for example, for some astrophysical scenario taken from, probably this is from Iliadis, if I don't remember wrongly. So anyway, we know that they happen into a region, which is the gamma peak region in stars, where most of the nuclear reaction actually occurs, because it's given from the convolution of usually a Maxwell-Boltzmann distribution of the ions and tunneling through the Coulomb barrier. So since we are talking about this cross section very low, as you know, so what we usually do, we do extrapolation, we build, we try to suppress underground, the background by going underground. And so the idea is now to, I mean, since a couple of years, to try to explore nuclear reaction of astrophysical interest directly in a laser-induced astrophysical plasma, laboratory plasma, sorry, which can somehow can mimic the interior, some astrophysical, let's say, scenario. So the technique is the Coulomb explosion of cryogenically cooled gases. So if you are able to cool a supersonic nozzle, a mixer in a supersonic nozzle, close to the, let's say, to the critical temperature, which is the temperature above which you cannot liquefy the gas, no matter how much you compress it. So the states is in the gas liquid transition. It is shown that these you clusterize basically the mixtures if it's possible to do it, if the temperature is suitable. And when a laser, high intensity laser, interacts with this gas, which is, for example, expanding in a vacuum chamber, it actually, this clusters has a property that absorbs the laser's energy very efficiently. So if you are giving hundreds of joules, you're actually having a good transferred energy ratio, if you want. So this is happening at this intensity and above 10 to the 16, some units of 10 to the 16. And is given, the energy is given to the electrons, which are stripped of this cluster. So these clusters are macro cluster made of macromolecules bound together by van der Waals forces, basically. So there is a huge positive charge when they are stripped of the electrons. So when you strip this, of course, this cluster feels the Coulombian force, the potential, and simply explodes. This is what is called Coulomb explosion in this case. So these ions in this paradigm can be accelerated up to multi-keV kinetic energies. For example, this is the campaign, 2 campaigns we did at the Texas UT, Texas Petaway Laser, some colleagues and us. And so where we delivered hundreds of joules into a, let's say, gas cluster through a supersonic nozzle of this gas was made of deuterium, or in some cases we had also helium-3 mixtures, but it's not important for now. So what we do is the Coulomb explosion, and so the deuterium clusters are, deuterium ions are accelerated, and if you manage to measure the energy distribution function of this deuterium, this ion, you somehow you will have some beam profile at some point, if you want to say that. This deuterium, of course, interacts with the surrounding deuteriums and also the surrounding gas, which is not be illuminated by the laser, for example, and of course undergo nuclear reaction, so the diffusion. And what you can measure is, of course, the neutron from the DD and the proton with roughly 50% branching ratio. So this has been done since the year 2000 up to some years ago, when then the Petawatt closed. But so assume that we managed to measure these deuterium that are accelerated. So we have some information about the target itself, which in this case is the one that is not accelerated, or it can be the other deuterium which are accelerated. So the center of mass energy spans from, let's say, from 0 to the maximum. If you can measure, for example, let's focus on the and helium-3. So if you can measure the neutron, which are ejected, the reaction from the output of the reactions comes out, that they are very, we know that are 2.45 neutron plus the energy that, of course, it is in the center of mass, okay, whatever. If we measure this with an array of neutron detectors, for example, and if you measure all the other things, so the yield of the neutrons, we have information about the plasma itself that is created, and we measure the deuterium energy distribution, we can actually infer some information on the cross-section here. Forget about the BB, which is written there. So in this case, we had 1 Faraday cup to measure the deuterium distribution. So in time of flight, neutron in time of flight, and we have some diagnostic for the plasma, or some models in some case. So this is a typical spectrum that we have from the Faraday cup, for example. These are volts, this is microseconds. And we can say that there is a huge X-ray peak, which is a problem for us, of course, because it's still going close to what is our accelerated deuteron peak. But if we, and then we have some slow ions that are not accelerated outside the cylindrical plasma that is created by the laser. So if we transform into the energy spectra here, and we have energy, we can somehow subtract the background due to the X-rays with some techniques. There are different approaches. The good thing is that anyway, even if this process is not properly thermal, as you can imagine, the actual deuterium distribution is well described by a Maxwellian curve. So it's, to say, thermalized somehow. And we have a temperature there. So we are also able to establish something which is related to the most probable energy, let's say, or let's say the window energy in which these reactions are occurring, which is somehow related to the gamma energy, but of course it's in this different environment, so it's not the same. And we can actually, so by combining, let's say, the time of flight, different time of flights, we can extrapolate some information. We can evaluate actually, for example, the astrophysical X factor, which is written there. We have seen this a lot of times, so I will not go through this. So we can give some information here. The problem, of course, is always the X-ray that are generated by Bremsstrahlung X-ray, mostly X-rays, mostly due to the electrons that are actually escaping around, and so they do a lot of X-rays, and the electromagnetic pulse noise, which is damaging complex electronics. So everything here is very simple. Most basic diagnostic and detectors that I can imagine is just scintillators and a Faraday cup here, which are not too much affected by these issues. So by doing this, you can actually have some results, and we managed to get some results. Here there are other that I'm not showing now, so I'm just showing this for the DD reaction here. So we managed to evaluate the astrophysical X factor in this energy range, and it is possible by tuning the nozzle, let's say the gas temperature and properties, to span different energies, because if you are able to control it, and actually you will, or anyway, you are able to calculate this energy, you can somehow span an entire, let's say, up to almost 100 keV probably, and down to lower energy for sure. But here the cross section is low, so you need a lot of, let's say, shots, because now the technology is actually advancing, and we are having a lot of petawatt class lasers, which also have high repetition rate. So this one shot at Texas is one each 2 hours or something. So one shot, and you have to take everything. Everything must be good. You have to be sure that all of your experiments, your detectors are fine, and so on the other campaign that we did just before it closed, actually for some time, the Texas Petawatt, we actually went with some more detectors, and what we found out is that we found a dependence on the temperature at which the mixture, the gas was prepared. So it looks like if we get close to the critical temperature, we have an effect in the increase of the fusion by half order of magnitude, or so, maybe more. So it means that in this, so the preparation of the target is crucial in this kind of experiments. So this is so what has been done so far. What we are planning now to do is to do a systematic study of different reaction. And this is, I will not explain this because you know better than me. And I think that you already discussed electron skinning enough. I guess in this, I wasn't there the first day, but I think that you already know that the charge of you know better than me, the electron can shield the charge, and so you can get an enhancement in the fusion yield, let's say, in normal, in the standard nuclear scenario with accelerator and targets, where you have electrons that actually shield, so you have an enhancement. This enhancement can be, of course, somehow be factorized here. It's somehow proportional to this. We know about this. This is the potential, the screening potential. So if we are able to measure the cross section, let's say, or S factor in plasma, we have some information also about the screening in plasma, in laboratory plasma, which somehow we can relate to the screening which happens in stars, of course, which is different from what we have, for example, both from standard experiments and from indirect methods such as Trojanov's method, which give the bare nucleus cross section. So if we have all this information, for example, we can combine them and actually try to tackle a problem which is, I think, affecting a lot of our measurements. So I will just throw this here because I don't have much time, I guess, left. But for example, one that we could study. I don't know, maybe there was some discussion about that, but we know carbon 12 is a key reaction for stellar evolution, and you know better than me. We know about all the measurement and all the problems. And this is, for example, an scheme of the effects in different scenarios, so different densities of the effect of the electron screening on this reaction for lower energy, for the lower energy part especially. So we know that we did some studies with we have a mixture with carbon that could probably work, and we could actually measure this. The point is that we can do it now because now the technology advanced enough so that high repetition, high power laser also are available at almost at commercial, let's say, level. So to do this, we need a different approach, because we need an array, multi-diagnostic, let's say, for which is able to give all the information that we need. So we need, of course, this nozzle. We applied. We need, of course, an array of neutron detectors and an array of charged particle detectors, and we also need some way to discriminate, other ways to discriminate between species, ion species. So the Thomson parabolas. So these are, for example, what we applied for funding, and we are still waiting for an answer. We hope to get an answer soon, because time is crucial, I guess. But anyway, the more we advance, the more we think of other things that we could do and add to the project. So simply put, the nozzle is something like that. We can characterize the nozzle by using Rayleigh scattering, which is simply scattering of light by particle. And this is related to the size of the particle. So you can actually characterize your target in this way using Rayleigh scattering, and this is done already. We can, of course, we have our neutron detectors. We have some experience in that. This is, for example, for the last campaign, we had an array of like 10 neutron detectors. And as you can see, it's not always good signal. Sometimes the EMP, and it's not very visible, sorry. But sometimes you don't have a clear signal. Sometimes the tail is too long, for example, for the Higgs, and it's overlapping. So we did some studies. We also tested with a plastic scintillator, which is in a way giving different results. It probably is a better choice for us, but we are still doing some R&D on this. And we need to measure the charged particle. Since we will have more species, usually mixtures, so you need some techniques. So what is used is usually diamond detectors in time of flight and silicon carbides in time of flight. So these are two examples of two spectra. On the top you can see it's the amplitude of the signal and its time of flight, and if you reconstruct in the energy per mass, say, you can actually disentangle which one is the, for example, for DD in this case, so it was not so complicated, which is one is and the other one were contaminants or other things present in the target. And why these two detectors? Because this is a highly high electromagnetic background environment. So you need radiation hardness. So you need a lot, and you need especially fast detectors, because you need, for example, for these photopics, the detectors must recover very fast. Otherwise, it will blind everything. And these are silicon carbides taken from these articles. This is a bit okay. I don't want to comment more, but if you have, for example, you can also try to fit with some methods different charge state of the carbon that you are accelerating in the mixture. And but this is alone, this is probably not enough. So what usually is done is to use a spectrometer. And the most simple spectrometer is made by some magnets, Tesla or less, and some electric plates. So you apply voltage, and it's a simple spectrometer. Then you have to read this somehow, and usually you do this in a passive way. You have these imaging plates, and you have the impressed phosphorus screen or something. But lately, a lot of use has been done for the microchannel plates, which is actually very good detector because it's strong enough to resist, and it's giving good results. And this also is online. So you have, if you have a high repetition rate, you don't have time to change the image plates and change and put the other one. If you have 1 second, 1 hertz, for example, you want something online. In 10 seconds, you have to know everything. And there is a way to calibrate this. I will not go further in detail, but it's very clever to do how they did this at the Queen's University. So this is a timeline of what we think that we can do, actually. So I will not go in detail, but I think that now there is really a huge opportunity, because it is now the time that laser technology is advanced enough to allow systematic studies, which are needed for nuclear physics and nuclear physics in general. And there are many facilities around. Some of these are just the one that we did the experiment with. Some of the one we did the experiment, we know that we could use. And of course, some of these are part of INFN. We have one at LNS, one laser, that someday will be 1 petawatt, but we don't really need 1 petawatt. We can also work with half of the power, I would say. And of course, there is flame, and there are the laser of Eupraxia, which are in the future of Frascati laboratory, which are devoted, both flame and Eupraxia, mostly to electron acceleration. So it's not mostly it's due to wake field acceleration. So it's not something that we are going to explore much for our point of view of nuclear physics, probably. Unless maybe there is something, but I mean, the paradigm, the setup of the laser is such that since it's a gas target, do electron use gas target, we can use this. We can put our nozzle there, can cool it, and we can do it. And we are actually working on this direction now. So the conclusion. I hope I was fast and somehow clear, even if it's not exactly your cup of tea. So high power laser is actually doing a lot of developing. And now we have this opportunity to study nuclear reaction of astrophysical interest directly in plasma, which we can also characterize with diagnostics. And in our opinion, as a group, these laser cluster experiments is the perfect paradigm for nuclear astrophysics because of the energy range that we are exploring, and because of the control that we can have on this experiment with respect to other techniques which are mostly suited so far for let's say other kind of physics, applied or higher energy physics. These so measurement of cross section are already done. We did it. Many people did it. The electron screening studies is something that we are hoping to be able to do. It's something that it's worth trying to do, at least. And of course, these screening studies will go in the direction of other researchers that are studying electron screening, starting from Luna, for example, and also the other groups which are studying electron screening in the what's the name of cos'è, Lubiana? Yes, exactly. So we have, I'll say, we are trying to attack this problem from different directions. At some point, I guess we will have some results also for the plasma, let's say, environments. But to do this, you need this kind of approach. You need detector which are suited. We need some developments on some detectors because it's a very different environment with respect to the ones that we are used in normal nuclear physics experiments. And so we need money and people, of course. Thank you.
Thank you, Dario. The error bars in your ability are large. How is calculating the cross section? You know, cross section decreases exponentially when the
You mean here?
or the T plus the data that you showed.
So they're actually
Here?
reaction rates, right?
Yeah, the error bar.
Yeah, you can actually, sorry, one question, because I'm already, so the action bar here or here? Yeah, yes, yes. Can we zoom it?
Large.
Yes, because statistics, it does.
The large error bar.
It,
So, do you think that you can improve this part?
yes, it's statistics problem. So if we should,
It's not statistics, it's the energy.
yeah, but these are, but if you measure, so if you measure one reaction, you have 100% error. If I do one shot, I measure a lot of reaction, but
You have to be
But-
sure
but-
about
but-
the energy when you do that.
yes, this is how we, okay. This is how we actually, what is minus here?
Dario, you're not measuring cross sections, you're measuring reaction rates.
You don't care.
Because you say you have a distribution of energy.
Yes,
And then you're integrating this cross sections for the, and then you're getting reaction rates. You should plot actually reaction rates, is that correct?
Measuring the temperature. The temperature was on the upper scale.
Yeah.
The range was on the gamma plane.
Yeah, but in that case, the energy spectrum that on which you have made a measurement, how is taken under control? So you know how well you know the energy spectrum.
so this is the energy spectrum. So the energy spectrum comes from here. So this is just one shot. This is my energy spectrum, but this is just one shot. That's the point. So what you do is that you, sorry? This is the deuter energy spectrum.
Yeah, but you fit that with the Maxwellian.
But the point is that you can fit this with the Maxwellian, so you relate just with the temperature. The sensitive part is here, of course. Here, when you have to disentangle the background from the X because they are mimicking your higher energy deuterium, which will give you the higher output. So you will have, so this is the delicate part. But at some point, if you do a lot of measurement, you can also,
So you decompose it somehow.
you have to, yeah.
Well, you had several steps there when you get, so how do you know this second step is the hitting of the electrons? They are hitting, not thrown away by the laser.
That's interesting. So the electrons are temporarily removed, but
Yeah.
they're not just disappearing, of course, they are still there. So it's interesting to study this. If you have some diagnostics, which is fast enough, for example, to have some imaging of your electron density, you can also monitor it. It's not easy, of course, but there are techniques that can allow you to have a temporal profile. I don't know about the time scales, maybe they are too fast, but some indication maybe you can have. I mean, not say 10 100 picosecond level, you can have this information.
And then you say hitting of the clusters, and then you get this distribution, which is Maxwellian of the deuterons that are in. Okay,
straight. I mean, you get rid of any spectroscopy study.
Yeah.
It's
I mean, you
measure
do-
reaction rate.
Yeah, you do reaction rates. This is what, I mean, everybody's measuring, we know to measure cross sections. And then we integrate this and then say we have this reaction rates, which are used for all calculations.
Yeah, it's
So now you.
I can
have
imagine.
them-
I can imagine it's not straightforward to take these and then put it into stars because you have some, for example, some density difference mostly of the time.
No,
Yeah,
but the
the
reaction-
reaction rates is the same, depending on the temperature. So if you have a Maxwellian spectrum, like for a given temperature, yeah, eventually you have to repeat the calculations for different temperatures and reduce the. Only
You can change the property of your.
Yeah. you should-
But this can do it.
Your laser or whatever and changes the temperature of the
Yeah.
plasma, so
Yeah.
then you can do sigma years.
Yeah.
Instead of changing the energy, you change. the
So the
temperature.
Yeah.
comparison is reaction rate.
You should change the temperature.
Yeah.
No,
Yeah, this is doable. I mean, it's controllable at least.
Yeah, but then do you have an idea about the temperature that which your reaction rate? Do you have an idea?
Sorry, excuse me.
You've done the experiment.
Yes, I mean, if you fit these, it will be between. So it depends. You can go from 5 to, I guess, 20 is in temperature, keV or something like that. Maybe more if we.
Then you are actually at the temperature of the sun. So it's basically
Yeah.
that. So you can decompose or you give directly the.
The reaction rate is more straightforward.
Yeah, maybe, yeah, maybe yes.
Just call it, but then the error on the reaction rate, which is slightly large.
Well, not really. Well, the point is that yeah, the cross section will go low, but if you are actually, so the point is this: you have 100 joule of energy. So this 100 joule of energy can go to, let's say, very energetic spectra of deuterium, or let's say lower energetic spectra. But the amount, if you transfer the same, you have a huge spectra, higher yield. So somehow you can balance, I guess. So that's the point. So not doesn't scale directly, of course, because there are mechanisms, but the energy is this. So either you have a most the integral is what you're doing. So either you have the, let's say, lower yield but more energetic, or you have higher yield and less energetic. That's what you usually see also with other mechanisms like that. So this is another mechanism, but still is the I mean the point is similar.
Andreas?
To go back to the slide with the cross section on the right side, so you need it from you.
Okay.
I mean, I don't know anything about what you do, of course. But you say, depending on your cluster, you get a widely different yield, right? So how do you know that your cross section is actually what you have there on the left?
No, these are two different experimental campaigns. Sorry.
But your cluster has always, your cluster shape or whatever has always an effect, no?
My cluster what?
So you did the cluster thing, or the temperature, whatever other environmental conditions it is in. That has influence on the shape, no?
Yeah, I'm not following.
It's so well controlled.
Yeah, we
It's
have a nozzle with a high pressure and low temperature. We can change the pressure and the temperature of the nozzle. But we can also add, for instance, carbon to change that if you want to get higher temperature. So depending on the temperature, which is similar to that plot on the left, that plot refers to the temperature of in the nozzle, not of the plasma.
yes.
So the temperature in the nozzle, if you change it and you're at the critical, for instance, pressure, you can get closer to the critical temperature. You change the property of the plasma. They can get bigger, like 10 to the 3 particles to 10 to the 5. So when the laser arrives, it subtracts all the electrons and all the ions that remain all of a sudden positively charged, and they explode. And since the clusters have different size, the system is fully chaotic and then becomes the temperature. I don't know if that makes sense.
And the big class-
And you can change.
So this is
Can change the property. At the nozzle or the laser, you can give less energy, more energy, you can increase the pulse, duration, etc. And you can change the focal spot and so on.
to be
That's how we did at that time. Of course, at the beginning, we didn't know what we were doing, so we shoot many
Yeah.
times and then we look what the temperature is.
Yeah, so to be fully honest, you don't have full control of what's happening in a laser cluster experiment, but you can monitor everything. So you are planning to go to this temperature, and this you are planning that the laser is actually doing this very nice. It has a good contrast and it's interacting exactly as you want, but it's not always like that. So there is some stochastic factor that happens. That's why you need high repetition rate. But anyway, you control these things. That
Then you can do something that like NIF has done, and actually NIF has used Luna data, because they somehow calculated the cross-section of the PD and they controlled and they checked the results with our data
exactly.
to determine the temperature, to be sure that the plasma is at the temperature they took. So you can do something similar. You can take something which is relatively well known, then you can find a way to get your section to be sure that you have a good control of temperature.
Yes.
We did exactly the inverse of what you were saying. We assume that there is we don't know the cross section for some reason. And we measure the temperature of the plasma. This is one method to measure by looking at the distribution of the plasma directly with the Faraday current. The other method, or many other methods, you mix two quantities, for instance, deuterium and helium-3, and you measure the number of protons and neutrons emitted, and then you take the ratio, and that gives you the real temperature of the plasma.
Okay.
And the two things are exactly the same. So once you know what the temperature is, then you can calculate the sigma B, even if you don't know the cross section.
Yeah, that's good. When you have
And then we compare to.
but then you can get the rate, the cross section. But when you know the temperature, the distribution of temperature, then you have everything in your head. So it's true that you get the actual rate, but then you can decompose it and get it the cross section.
But if you want to study the screening effect, you are obliged to go, to go from the rate to the cross section. And so there is an error bar there that will come from the. Yeah, if you want to measure the spinning. If you want to study the spinning effect. Depends on what you want to do, but essentially you get reaction rate in the sparks somehow. Yeah, but because you have a plasma, you have a spinning which resembles the one you have in stellar plasma, so you don't have to make any correction.
Right.
Yeah, if you take the rate, but if you measure the rate at the right temperature, because here the measurements are at higher energy than
But we can
energy of
decrease
difference.
the temperature.
Yes, that's the point.
Yeah, you can do
I mean, actually, this is so previous experiment. For example, if I remember properly, these two were with 100 terawatt laser.
Are you going to do it? To go.
Yeah, sure, of course, that's the point.
That's where they find.
That's the point. That's what we're discussing. When you go to low energy, of course, you will have lower cross section, so you need more. But the point is that if you are able to transfer the energy more or less in the same way, you have this energy which is like that. You just put it here if you are good enough, if you are lucky enough, let's say. So you have also an increase in the yield, hopefully. But these two, for example, I was saying that the first is very low power laser. It's 100 terawatt laser, and it was like this 5 kV or couple 2 kV, 5 kV temperature. And it's also easier, to be honest, because you also have less gamma and X-rays, and the signal is clearer, to be honest. So it becomes a systematics too. That's what I'm trying to say, hopefully.
There are other methods to induce nuclear reactions with lasers,
Yes.
but not always Coulomb explosions.
No.
What other methods there are?
So that these are the two more common ways. So in this way, you just accelerate So you accelerate ions and then you have another target. This is not in plasma measurement anyway,
That's
not really.
Plasma, right?
So there are some other, so what they do at NIF, it's actually, yes, it's but it's different, completely different. So they focus under 92 lasers, very high power lasers, long pulse lasers. They compress a capsule, you know, they make X-rays. So they lose in this 99 efficiency, something like that. So these energy converted into the X-rays are compressing the fuel, the TI's fuel. And so it's actually triggering TT reaction by this, but it's a radiation pressure confinement actually. Huh?
This is more by this ignition by compression rather than by.
Yes, yes.
It's like perforation, no.
The temperatures are about like
Yeah,
Yeah.
okay.
But at least, can you have everything under control? So which one of the two can? Oh, I understood that this is very much reliable, even if you don't have a very power.
Yeah.
And how related.
Well, and if they have a lot of diagnostics, but a lot of diagnostics, a lot of money on NIF, so they control the. It's different. One shot at NIF takes I don't know how much, 1 week. Yeah, but preparation. So the point. Yeah. So the perfect shot is once in a year, I guess, for now. So because the point of NIF is that everything must be, so they have 192 lasers that must converge exactly the same, I mean, the same time, and it's not easy. The target must be perfect, must be flawless, because otherwise it will lose a lot of energy. It will not be enough to ignite and so on. So at NIF is a different story, but I mean, NIF is a 30-year program, I guess. They started funding 30 years ago. 20 something, yeah.
We have another, since we're doing that over time. So in China, we have 8 laser beam, not similar to NIF, and we had about 20 kilojoules. And so we got included this 20 kilojoule direct on target. So the NIF is indirect drive with the direct drive.
Yeah.
And we compressed this guy to very high compression. The only difference was the temperature was 1 dB, even less. Number of fusion was not so high. Then we had
But there was.
then we had a 9 laser beam that was a picosecond. The 8 one were nanosecond. We had a 9 laser beam petawatt picosecond. And we compressed, and then the 9 beam target like we're saying NSA, and we shoot a bunch of proton deuteriums from there. So compression and the engine was a 2-stroke engine, if you recall the nuts. That was the idea, compress and ignite. So we compress, and we got an increase in the number of fusion. Not too much because we only had the temperatures, but the compression was very high. I think we reached even higher than NIF, because they are not they won't compromise between temperature and density. As you know, the cross section goes up very much with the temperature. So if you are 1 kV, it was a lot. And so they did the compromise. We tried the other one. So compression was high, but the method of ignition was not. But we think if you have many lasers that you can then send lots of this high energy deuterium, then the thing is going to explode, and eventually it's going to get much more fusion. But of course, it's a great thing we did before COVID, and we stopped.
What was the temperature of NIF?
And NIF is about between 5 and 10 PV. And I think they compress like 1,000 times.
Okay.
And now they even included the magnetic field. So when we did in China, everything exploded. And so I think at the last step, they on magnetic field together with the compression, and then combine the particles a little bit more, and they got this skin and this.
The CNN result.
Yeah.
That's great.
But you mentioned also carbon 12 plus carbon 12.
Yeah, for example, that was just
200 meg.
At so low
in principle.
temperature.
Well, we never tried, to be honest, because we didn't work with. I mean, we had carbon, but we didn't see carbon accelerating with our. So it depends whether the carbon clusterizes enough, so you can actually clusterize it. We are confident to be doing. So if we are able to do it, we can control it.
No, my question was that carbon 12 plus carbon 12, the interesting temperature region would be higher, right?
Yeah, but this is
So I
but-
mean,
that's true, but it depends on the paradigm. For example, okay, this is another paradigm. It's not Coulomb explosion because no one has. I never see some carbon spectra from Coulomb explosion. From cryogenically Coulomb explosion, but this is another paradigm, for example. And or if I show you maybe here, there was directly the so these, okay, it's not energy, so we cannot relate, but in principle, these are MeV per nucleon, for example, I guess. So it's very high.
so you can.
It is very high.
you can
So
go higher.
we never tried, so I cannot tell you if we can make MEV carbon.
Yeah.
It's like, yeah, but this is RPA, so it's a different.
But some Japanese group had accelerated with the clusters, and they say 100 MeV total energy for carbon. For proton, you get maybe 30 to 40 MeV so far. Those are experimental data, which I thought those were your data. And they, nonetheless. At 2 weeks ago in Spain, we got about 40 MeV proton.
Yeah, but this is different. I mean, I'm not interested into this kind. Or I mean, we can discuss about that, but I'm not really interested in some kind of spectrum that's going like the equitable energy tail like that. Maybe I don't know.
So that's something different, yeah,
Yeah, it's something different.
something different.
Okay.
That obviously takes the target into.
Yeah.
Thank you. Thank you. We can call the speaker.
Thank you.